Hello there guys, welcome back to another epic inexorable maths video. In this video, we're looking at finding the arc length of a curve, and I'm not talking about the arc length in a circle. I'm talking about this name that we give, basically the length of a curve. We call it the arc length. A little bit confusing, but that's what we call it. So, for example, if I had 2 points A and B on some arbitrary y equals f of x, how would I work out the exact length from A to B, the exact length along the function? How could I do it? We're going to need to use some calculus. So let's just dive straight into how to do this. I'm going to consider a point here, P, and I'll just say that it has coordinates x and y. So it's an arbitrary point along the curve. I'm then going to choose a point that's relatively nearby to P, and I'll call it Q. And so Q is just going to be, it's going to have the same x coordinate as P, but it's going to have a slight shift in the x direction. So it's going to be x plus delta x. Delta x is just a small change in x. And the y coordinate will be y plus delta y. Okay? So if these are close enough together, we can do something quite cool. Okay? Now, if I say that the actual length between these 2 points along the curve is, let's say, if I call this delta S, okay? Because S is normally used for this, by the way, guys. Sometimes you'll see an L, but I'm going to use an S, okay? A small change in the curve, in the length across the curve. Then if I approximate this by a straight line, okay, like that, so that's a straight line, because I'm making a very small triangle, a very small right angle triangle, then I can say that delta S squared is approximately going to be equal to delta x squared, because that's the change in x coordinates between P and Q, plus delta y squared, because that's the change in y coordinates between P and Q. So it's not exactly the same, because delta S is the actual curved distance, whereas we're only approximating it using Pythagoras and a straight line, so it's only approximately true. But hopefully you can see that as these delta x's, delta y's get smaller and smaller and smaller, as they approach zero, this actually becomes an equality sign. So if I say they are infinitely small distances, and I rewrite them as like ds, dx, dy, then I can say that they are exactly the same. So ds squared is equal to dx squared plus dy squared, where all of these are arbitrarily small as we take the limit as delta x goes to zero, basically. It's a bit hand-wavy, but this is the explanation I'm going to give you for now, because this is not real analysis, this is not analysis, so this is the explanation that I'm going to give you for now. Otherwise, it gets really complicated the rigorous way, but hopefully this is satisfactory enough for almost anyone. Okay, now we're trying to find what S is, okay? S, not like ds or anything like that. So what I'm going to do is I'm going to divide both sides of this equation by dx squared, and you'll see why in a second. So I've got ds dx all squared equals 1 plus dy dx squared. I've divided both sides by dx squared. Then I'm going to take the square root of both sides, assuming that both sides are positive, of course, and I'm going to get this. And that's supposed to be a y, but it's drawn very badly. There we go. Cool. And then I'm going to integrate both sides with respect to x, okay? So I'll do it down here. So the integral of ds dx with respect to x is equal to the integral of the square root of 1 plus dy dx squared dx, and that is a y. Lovely. Okay, cool. Now we need to put some limits in here, because otherwise we're going to have like some plus c business and all of that stuff. So I'm going to define the point A to have coordinates, let's say xa, ya, and B is going to have coordinates, let's say xb, yb, like that, okay? So I want to integrate this because I'm integrating with respect to x, from xa up to xb. So from xa to xb. From xa to xb, okay? And what I'm going to get is, if I go over here, this expression here, obviously ds dx integrated is just s. So I've got s on its own, evaluated from xa to xb, equals the integral, again, from xa to xb of this expression, the square root of 1 plus dy dx squared dx. Okay, now s is a function of x, so you can kind of plug them in and all that stuff like that, but we are going to just say that this is definitionally what s actually is. So this is just s, okay? You might say, what? Shouldn't it be like 0 or something? S is a function of x, so it's like s of xb minus s of xa, and I'm just going to call that s, okay? If that makes sense. And so s, which is the arc length, is just the integral from xa to xb of the square root of 1 plus dy dx squared dx, okay? That is the idea. That is the formula for the arc length, okay? Now, to see it in action, because I think an example would be super, super useful here, let's go and do an example and see what happens. Okay guys, so we've got an example here. Y is equal to 1/3 x to the power of 3 over 2. Find the length of the arc from x equals 0 to x equals 12. So in other words, I've drawn the graph for us already. Let's say that this is when x is 12. The idea is, what is the exact length of this curved line? That's the idea. Okay, so we're going to use the formula. So again, the formula is that the arc length s of any curve is the integral from the starting value of x to the ending value of x, and we're integrating the square root of 1 plus the derivative of the function squared, okay, dx. That's the formula for the arc length that we call s, okay? So in this question, we're going to need to find dy dx. It's always good to find dy dx first. So the derivative of 1/3 x to the 3 over 2 is 1/3 times 3 over 2, so 1/2, times x to the power of 1 over 2. Hopefully that makes sense. And then, if I square this, or let's just go straight into the formula, s is going to be equal to the integral from, again, we're starting from 0, ending at 12, so the integral from 0 to 12 of the square root of 1 plus, and it's dy dx squared. So 1/2 x to the half in brackets squared. Okay, and if we do this integral, that's going to give us the answer. So this is equal to the integral from 0 to 12 of the square root of 1 plus, and then obviously x to the half squared is just x to the 1, but then we have a half squared, that's going to give us a quarter. So it's 1 plus a quarter x dx there. And again, we have to actually integrate this, so excuse me while I go up here because there's no other space. So what is this going to be equal to? Well, this is 1 plus a quarter x to the power of a half. So the thing that would differentiate to that is going to be 1 plus a quarter x to the power of 3 over 2, and then maybe times a constant. So let's just, in our heads, let's just differentiate 1 plus a quarter x to the 3 over 2. That would differentiate to 3 over 2 times 1 over 4, because chain rule, times 1 plus a quarter x to the power of a half. So in other words, this is 3 over 8 times 1 plus a quarter x to the power of a half. Now we see that this is giving us what we want, but there's an extra 3/8 on the outside, which we didn't want. It's not there. So the actual thing that this integrates to is 8 over 3 times 1 plus a half x to the 3 over 2. Hopefully you see that if I put this here, then there's going to be an 8 over 3 here, and they cancel out, which gives us this. So in other words, this thing here is equal to 8 over 3 8 over 3 times 1 plus a quarter x to the power of 3 over 2, like that. And again, that's from 0 to 12, okay? And let me just clear the board and we can continue the working out. Okay guys, so I've left the diagram, I've left the formula, but I've just moved everything up here so we can continue. So obviously at this point it's just some, I would say relatively simple integration business. So it's 8 over 3 times 1 plus, and this is a quarter times 12, so 3, the number 3, to the power of 3 over 2, minus 8 over 3 times 1 on its own to the power of 3 over 2, like that. And this is equal to 8 over 3 times 4 to the power of 3 over 2. 4 to the power of 3 over 2 is 4 to the power of a half, so 2, and then to the power of 3. So that's just the number 8, minus 8 over 3, and then obviously 1 to the 3 over 2 is just the number 1. So this gives us 64 over 3 minus 8 over 3. And that's going to be 56 over 3, which is the final answer. Okay, so the exact length from the origin to the x-coordinate of 12 along this path, curved path, is exactly 56 over 3. Okay, so I'll do plenty more examples of this. Also, by the way, guys, I didn't mention, but you can also use that. You can do it in terms of y. So if you have a function that is not really a function, it's only a function in the y direction. So let's say you have a function that's, I don't know, going like this or something. How would you find the arc length there? You can't exactly integrate that very easily. You could integrate it up the y-axis. What about a function that's described in terms of polar coordinates or parametric equations? All of these have formulas as well for arc length. We're going to get into all of that good stuff and look at plenty of examples. So thank you guys so much for watching. As always, I highly appreciate it. If there's anything I can do to make the videos better, please do let me know. And another public service announcement, you will never, ever see a mid-roll ad on this YouTube channel, ever. I do not believe that you, as someone on this channel trying to educate yourself, should be interrupted by a pesky ad in this late-stage capitalistic society that we live in. If you're trying to learn something, you're not going to be interrupted by an advert. You'll see one at the beginning of the video before it begins. Once the video has started, if you ever see an ad on my channel, leave a comment on that video and I will delete the mid-roll ad immediately. I do not wish for mid-roll ads to be played in the middle of my videos. So if you ever see one, please let me know. You really shouldn't do it. So thank you so much for watching. As always, I highly appreciate it, and I'll see you in the next one. Cheers.